Hi friends, so we are into our 7th lecture of Prognostics and Health Management, a systems approach. I am bringing this element, that is a systems approach, because for complex engineering systems we must integrate prognostics, and that starts from conceptual stage, design stage, and then commissioning, operation stage, and then plant goes into shutdown after tens of years of operation. And then also there are some gap areas we find where especially about aging of the components, where we need to have prognostics and diagnostics. So the topic or the subject today is fault diagnosis and machine learning. Fault diagnosis, probably all of you must have heard about it. Whenever you build a machine and if it fails, and then you try to understand what are the faults. If you have power supply in your house, and if the power supply is not failed, then you try to diagnose the problem, whether it is overload problem, whether it is a short circuit somewhere, or some other fault related to end, like bulb has fused. How you know that? Because electricity passes through so many, it is junction failure, switch failure, breaker failure, many things. So fault diagnosis is integral part of our life. Then it is something like in factories also, when the machines don't start, we say what is the problem, and that is where the fault diagnostic starts. Or you hear an unusual noise from a machine, and then you ask your operator to stop and then try to do an investigation, because fault should not propagate into failure, or should not manifest into failure, because once failure is there, replacement of the components are required, and that takes time and all that. So let us repair it before that itself. Whether it is civil, mechanical, electrical, everywhere, fault diagnosis is an integral part of any system operation or maintenance. So in the first lecture, I'll introduce this subject in a little detail, and then finally we will go to the second, third, fourth and all that, because our idea is to learn the fault diagnostic techniques, and then how it can be embedded in machine learning, so that our systems, they come with the fault diagnostics available. Even condition based maintenance also is something which is related to fault diagnostics. So this week, in the context of fault diagnostics and machine learning, the first lecture, as I mentioned, it is an introduction, and then systems approach to fault diagnosis or diagnostics. I will be using these words interchangeably, diagnosis or diagnostics, And then, because this was so many techniques are there, so part A and part B are there. They are covered in part A and part B. And there is one more technique which has got its own self-standing. It's called root cause analysis. It's a very serious and very comprehensive analysis, because it is done in safety critical system, or mega system, where if the component fail, the stakes are very high in terms of risk, as well as in terms of the shutdown time, because once the plant shut down, deliverables stop, and that's how. So the idea is, once you do the root cause analysis and you have reached the root of the failures or roots of the failure, take the corrective action program, such that these failures, ideally speaking, if the root cause analysis was correct, and we were able to get the root faults, and that we have corrected, that means it should not recur, at least in coming time, maybe 5 year, 10 year or so. That means we say that root cause analysis done was very successful, because all those faults are not recurring. And even the feedback analysis will tell us that those faults are nowhere there. And then machine diagnostic learning machine learning and diagnostics. We'll see how these diagnostics, they are implemented into machine learning. We will not be covering all the tools and techniques, but whatever coverage is there in this lecture, probably it will be sufficient for you. So, the background, as I mentioned, fault diagnosis is a very specialized domain. In fact, maintenance and operation staffs in any big company or a center, they are trained to do fault diagnostics. In fact, if you remove from the training the fault diagnostics, that means you don't have required qualification to operate or maintain the machines actually. And then what is the origin of this word fault diagnosis? To be very straight on this, probably human existence and fault diagnostics, they came around the same time, because your survival was dependent on how strong your protection is there, how strong your survival instinct is there, and that will be determined by some physical entities like your house, your tools that you are using. And if your fault diagnosis goes wrong, you end up into threat condition, and you no more remain in the safety paradigm actually. And then diagnostics and prognostics. In fact, diagnostics, normally it is said that it is either the failure when you start, or you try to see how the failures can occur, and you line up or embed them into machine, or you embed them into our training program, and that's how diagnostics bearing failure. You know that inner cage failure, outer cage failure, then ball failure, and many misalignment, all those things. So there are well established diagnostic tools and techniques that are available, and as on today, your diagnostic expert or a condition monitoring or in-service inspection expert can tell what has failed. These things, the learnings have gone so strong that looking at the vibration signature, they will tell you whether inner race has failed, outer race has failed, or balls, one or two balls, they have failed, or cage has failed. So we have gone quite a deep into it, even a human understanding of the fault diagnostic itself. This I am talking about bearing. This is true for even any other. Now, diagnostics we do in the current context, but prognostics is for the future. So in diagnostics we see how it can happen, and in prognostics we say when it will happen. It is remaining useful life. So prognostics is a future. But building a prognostic also, you require a lot of diagnostic knowledge. What you will embed into the machine. So you should have some ways, and I probably in this lecture you will understand how they overlap, diagnostics and prognostics. Then machine learning and diagnostics. Yes, it provides a knowledge of the plant or component or system built into the machine, and those machines, they detect there is something wrong, okay, online. So it becomes a support for the staff who are involved in operation and maintenance of the plant. And diagnostic tools and technique. There are techniques, some techniques just for the sake of completion we will do it, okay. So, and the root cause analysis, it is a field in itself. It's a very serious field, because sometimes you have to model theoretical studies here, sometimes you have to go for interview, sometimes you have to go for recording, re-recording, simulation, and in root cause analysis, I would say every diagnostic technique has got its role. So when I perform a root cause analysis, that means I am using the toolbox of the diagnostic technique. So if I have to tell what is the origin, so the immediate available literature shows that diagnostic or diagnosis has got its origin in healthcare or medical field. When a person approaches doctor, he will ask some question, he will do some test, and those things are called together in simple way diagnosis was done. So what was lacking, or what is the disease, that is found out, and after that only prognostic procedure starts. So the available record shows this. But then if you look at it in a very documented way or something, if you are hell bent upon seeing then Ayurveda, Greek philosophy, and Egyptian philosophy, they also showed there were techniques that were available, but they were mostly we try to see some examination which involves looking at your eyes, ears, skin, mouth, nose inspection, and pulse rate, of course. And then we all this thing ensemble of checking that was done. We try to say, okay, this is the problem, and then accordingly the medicine was given. And of course, if required, because in Ayurveda or in ancient Indian philosophy, there were techniques where even surgeries were performed. There are documented evidences that are available. So it was trying to do some sort of investigation to surgery. It was a full and follow-up. These were the procedures actually. And if we trace to the human existence, that means go much behind and try to see the human existence, so what all is required and what all you should understand things around you, how they work, how they don't work. If I have some tool which I am using during my when I go for hunting animals, so I should know how my tool works and how it can fail. So diagnostic things they were very primitive tool as it looks like, but then they were survival mechanism. So protections, whether you build your house, even if it is a mud house, we should know that it should not fall, it should not cause you. So that is the traces we have from the history. Even common sense will tell us that diagnostics was part of it. And then natural evolution occurred in diagnosis, informal way to in a very formal way. Again, we are going back into the past and trying to see rational based approach evolved, and protection from harm and all that will be discussed, and management thing came into existence. Okay, prognosis is relatively little known, but qualitative meaning of prognosis were used even earlier also. In medical term also, we might not use a very quantified commitment or statement of the remaining life, but doctors may say it is 3 years, 4 years, 5 years, and that may vary as the diagnosis progresses actually. So it has evolved from empirical science to experimental methods and finally clinical methods. So this is the evolution, and now it is on the shop floor. Clinical is a term which is used in the medical domain, and shop floors we use a term in industrial or engineering domain. And the defense. So somewhere along this healthcare diagnostic engineering diagnosis came into existence, probably starting with the defense and then engineering in general. Okay, so if you see science where it is being applied more, one is the life sciences, and then other one is the defense. So in defense, it is before it touches normal industry, it entered there actually, because in defense, equipment should not fail in the field, and that's how the birth of reliability also is in the World War I, when the equipment they were taken to the field and they were failing. So a formal MIL 217 or these standards, they took their birth, and reliability field came into the existence. Okay, so now if I look at the plant life cycle, it starts with the planning, design, commissioning, operation and maintenance, refurbishment. Refurbishment means extended maintenance is done on the plant to extend its life. So 5 years, 10 years, after 30 years or say 20 years or 40 years, the refurbishment program, so that we can operate the same plant, because it is a very expensive proposition to shut down the plant permanently. But if even after refurbishment, some 10 years or 20 years of operation, the plant is shut down, then decommissioning starts. And finally, the area which was covered by the plant, it is converted into greenfield. Okay, that is ideally it should happen actually. So The advances in diagnostics you can see all through during planning stage, when even we start the building the system, we are bothered about whether they fail more, less, and which is their weakness and all that. So in very then only we go for design stage, because once we decide, okay, our pump, motor, heat exchanger, turbine, they should be of this size, and for maintaining them we require a manhole, to inspect the tubes and all that. So provision for diagnostics is visualized right in the planning stage itself, and then finally once that conceptual things are there, then design stage things are come into picture. And in design, one has to find out the maintainability of the system. And maintainability, why? Because we should be able to not only do the fault diagnosis, we should be able to replacement should be done such that maintainability can be effectively seen along with the surveillance also. Okay. Then procurement stage, yes, we will go for selecting those components where there are provision for diagnostics, and now maybe time to follow, we will be asking for prognostic provision also, or condition based monitoring provision also. Okay, because condition based maintenance, they will give line of degradation or track of degradation, and then prognostics will derive information on the remaining useful life. So state of the art equipment down the line have to follow prognostics also. Commissioning stage, yes, once the plant is commissioned, all the things which are perceived earlier, they will be documented, and whether the fault can be removed, fault can be diagnosed. If there is some problem in commissioning stage itself, it will be fixed, because after plant gets into operation, it becomes difficult. And during plant operation, yes, we get the first hand experience of, and so suppose only still 5% or 10% areas will be, you will find that maintainability is not there, and that is where it calls for the updating plant, doing maintenance, and trying to do some backfitting something, so that plant is operable and maintainable. And refurbishing stage, it's something very important. Now we want to track the components which have operated for 40 years, but they will operate for 10 years. So we put additional sensor. It is very important in refurbishment stage, whether it is a machine or a passive component like pipeline or a vessel, we have to monitor them online, because their margins have come down, and we should not go to threatened stage, or we should not go to a stage where events can happen actually. Okay, so that's how it is. So refurbishment stage is very important. It gives feedback of last 30 to 40 years, and then some tools for diagnostics and prognostics are installed. So this is we are able to review the life cycle of diagnostics and prognostics. Now, traditional approach to diagnostics in operating plant, you know that there are two category of component. I have been repeating time and again. Process system and safety system, broad category. There are in between many categories: safety support system, maintainable system, non-maintainable system. There are so many, but let us put them into two categories. Why? Because process systems can be, they are continuously operating, so they can be in fact easily monitored. Even a small leakage, you will know, because the system was operating. If a motor is about to fail, or we will know their signature. If bearing was about to fail, we will know the signature that this bearing for a recirculation loop has some problem, and corrective actions are taken. So process systems, yes, online monitoring and all very, but in safety system, online monitoring will not help, because safety system remain standby. So if something is not operating, complete train of electronics, if it is remaining standby, then how you will know? So for this also, there are some special facilities are built, like built-in test. That means electronics is there. There is let's assume there is no current flowing from up to down end for actuation. So what do you do? So you start giving small impulses and see whether the circuit is all right. So this is called built-in test facilities which are for electronics. Similarly, for shutdown thing also, somewhere leakage or some if you want to monitor bearing, then physically we do the testing, that is called testing and surveillance. So for a small period they will be started compared to their full-fledged operation, and will know that and do the diagnostics whether it is all right or not. If they are not all right, then again a complete diagnostics follow. Why it happened? Because oil problem, or the bearing got aged, or inner race, outer race, as I mentioned there. So those things have to be fixed for a safety system also, and it is done during testing. Okay, so there is a called test and surveillance program that you have to follow, and that's how the diagnostics is implemented for process system, safety system. And if electronics has a different case, because mostly it is a passive component, so we have that provision. So diagnostics and prognostics. Before we come to the discussion, where is their overlap, how they different, okay. So just a small comparison, it will show that the analysis, if we say purpose, diagnostics, it is present health of the component, but in prognostics it is future prediction, that is future health. And go on doing tracking till it fails. So then we call it as a remaining useful life prediction, and then root cause analysis is a failure investigation. Okay, that failure should not happen, that component should not fail, and diagnosis, that if it is an incipient failure, we should catch in between. If it has failed, then we should take. So it relates to present plant operation and maintenance, while here futuristic. So these three, we see the overlap over here, because as I mentioned, prognostics also, if we build and embed into a machine learning tool, a complete diagnostic has to be done. Which component will fail, how it will fail, what will be its signature. So that knowledge helps us to build prediction module also. And let's say typical case to continue our discussion. We have a motor, bearing and a pump setup everywhere. It is such a generic setup which is there. So for monitoring the health of the bearing, we have vibration and temperature sensors are provided, and for the bearing, and this is a bullseye. Bullseye means there is a small hole with a glass which shows the oil level, if it is a oil bearing, and then it is called bullseye actually. And oil quality and quantity also you can check over here, both. If it is certain level, no need to worry. If it is more also, then also it is not good. If it is less, then also we have to maintain a minimum level where it can go up and down in a small band actually, So we have this setup, and if I have to talk about, a lot of work is going on in prognostics and health management of bearing, because bearings are critical component. If they fail, then the shutdown, extended shutdown might happen. Or if they are part of, suppose this is a part of injection system, let us say water injection for fire injection system, then it is a safety system. So then also if on demand it doesn't come, then also it is a problem. So it is better to understand the bearing first. It is a construction feature. So bearing is a very simple mechanism. It has got inner race, that is inner ring, then there is outer ring, the outer race, in between balls are there, spherical balls are there, and they are being held in position by cage ring. It is called, black portion is showing the cage. So now the science of vibration has come to this level. It can, looking at the signature, whether it is a frequency domain or time domain, we can make out whether it is a cage has failed, or one or two ball has failed, or inner race has failed, or outer race has failed. Looking at the signature without machine is operating, we can make out. Maybe in some lecture case studies when we discuss, we will talk about it in details actually. So, and then one more important thing is there. Sometimes motor current signature or voltage variation, dip in voltage and all, they also provide critical information about the health of the motor. So what we have seen here, prognostics and health management or diagnostics of motor, bearing and pump, and of course this piping and all that, and this motor current signature analysis we have. So this field is matured in the sense that using vibration signature or motor current signature analysis, we can find out what is wrong. These two white things are, one is voltage and the other one is current meter actually, which gives us online regarding. But during the prognostics, we have to have put some sensors over here for vibration and all that, because radial, axial, shaft misalignment, bearing, I told you, inner race, outer race, so many things you have to do this thing. And for motor, it is a motor current signature analysis and so many other things. Like sometimes there is a conductors are there, the insulation failure and all those kind of phenomena are encountered. We can see that. So diagnostics and prognostics, healthcare, it was inception was there invisibly. We can see in the near 100 years or so, and then in engineering, it all started. Some borrowed somewhere, and somewhere the engineering knowledge is set, and prognostics and diagnostics were started. Diagnostics that we do for present situation, and prognostics we do for future. It could be online or offline, both. Sometimes it could be between online and offline, in the sense that we carry some instrument, measure the vibration, so it is not online, but we put the sensor there, and that way we do for so many machines. So so that is also could be prognostic, but it will be sort of offline, because those signals are not coming to the control room. And then diagnostics also in similar way, and typical temperature for a mechanical system, could be vibration, corrosion, there are various mechanisms are there. And for prognostics also, having the sensor installed there, we can check its life, and how we can estimate the remaining useful life. So RUL is an integral part of prognostics. Now, if I do a comparison and try to understand, so the purpose of diagnosis is to detect whether online or offline mode, and implement a corrective mention program. Prognostics health for prediction of future conditions in general, but if you tell the objective, it is estimating the remaining useful life, so that management action can be implemented, and it doesn't remain prognostics, it becomes prognostics and health management. And objective here is to find fault and to isolate or remove the fault and take a corrective action. And techniques that are there, online, offline, both are there for diagnostics also. And for example, for electronics, I mentioned it is a built-in test facility that is provided online or instrumented such that we will know fault. A short impulse of microseconds are sent across that, so that the relay or something, whatever was an actuator, that will not come into action. So for actuation of the final relay, that means process will get disturbed. It requires a signal of more than 30 microseconds. So in 1 or 2 microseconds, that signal will be sent without disturbing the electronic card. You are able to know their conditions actually. And techniques here are remaining useful life estimation. It is based on the sensor or precursor parameter monitoring, and domain specific requirement. Diagnostics or prognostic, anything, it will not be successful till we have domain specific knowledge. That means domain experts should be there when the diagnostics are being modeled, or prognostic should be modeled. Having a machine learning expert alone is not sufficient. For a quality diagnostics, you require a domain expert. So for like maintenance, you should have a maintenance expert. For operation, you should have operation expert. And for same thing is true for prognostics also. Science and technology, it is diagnostics have landed into engineering labs, and online monitoring are adequate. But resource consuming, prognostics is a resource consuming, because it requires huge computational AI tools, and then maintaining those things and all. It requires a huge data acquisition system. Sometimes it is cloud data, we are operating on cloud and all. So Internet of Things, they come into picture. So these are the things that are required. Attention on trend and past till present, what is going wrong, or how it is evolving. And it is here the question is when. when this component is going to fail. So that means that will give us a definition of understanding of remaining useful life. Okay. So now everything we are trying to say, plant risk and reliability we are reducing. What is the role of diagnostics in risk and reliability? If a component fails, then reliability comes down. If a safety system fails, it manifests as a risk parameter. Okay, both are part of risk reduction program also, and both are part of even increasing the reliability also. And in turn, how it is achieved? It is achieved through increasing the availability and maintainability. Risk reduction is realized through reduction of postulated accident into the initiating event. The frequency of initiating event, that means if we are reducing, that means we are increasing the plant reliability by removing unwarranted failure trips or failures. There is a need to pay attention to common cause failures and human factor. Somewhere we will be touching upon in diagnostics module itself how we can work about the because otherwise there are empirical things and empirical data that are available, and we are working with them. So what we can do something better, and of course human factor prognostics is very important because it is again one of the common cause factor into diagnostics and prognostics and in reliability as a whole. Machine learning in diagnostics, the artificial neural network, which has made a mark it manifested as a deep learning approach, and then support vector machine, expert system diagnostics, they are used extensively. It is a crisp rule based or fuzzy rule based, and then statistical methods are there. Of them, Naive Bayesian approach. We will be discussing one example also on this. So with this. We can say that we have seen the background of diagnostics and machine learning, plant life cycle and diagnostics, what it means, system context to diagnostics, why we should have a systems approach actually in diagnostics, and major features of diagnostics, and of course what are the overlapping area in diagnostics and prognostics. They are not in isolation. Of course they have deliverables in the present, and one is another prognostic is for the future. So popular machine learning methods, they form part of it because now they are implemented either as a machine learning or as a deep learning approach.